Well, friends, the last lesson of our 6th unit together in AP Calculus BC deals with other applications of the definite integral. We're going to take a look at work, and then when that's all done, we're going to take a look at the normal curve. There are others, but I want to take a look at a couple of other applications of the definite integral. Work is a concept from physics. In physics, we learned that if there is a constant force applied to some object over some distance, so I push on a refrigerator with my 175 pounds of body weight, and I move that refrigerator, I don't know, 2 inches, then that product represents the work that I have done against the refrigerator. In physics, work is force times distance. Of course, in high school physics, this force is always a constant. But what if it isn't? What if the force is not constant? Well, then we have a problem. So what we do is we say, well, let's break up our distance into tiny little changes in x, and then we assume on each little subinterval the force is a constant. And so you add up a whole bunch of works on a whole bunch of teeny tiny subintervals, so that if the force is variable, we integrate the force function dx. It's the same process we've always used. Break up the distance into teeny tiny subintervals, assume on each tiny subinterval everything is constant. Add up a whole bunch of works, add them up, Riemann sum, turns into an integral. Classic. The classic example is something called Hooke's law. Hooke's law applies to springs. For a spring, the force necessary to stretch the spring is proportional to the distance that the string is stretched. Yes, very good. So, suppose it takes a force of 16 newtons to move a spring from rest to 3 centimeters beyond rest. How much work is done to move that spring from rest to 6 centimeters beyond rest? Seems like it would be a simple problem, and sure enough, it is. Hooke's law says that the force applied to the spring is proportional to the distance it is stretched. So 16 newtons of force is K times the 3 centimeters we stretch the spring. So K is now 16/3, and we have a force function. I want to find the work done. Well, work is the integral over the interval of the force function applied over the distance. So what is that? That's 8/3 x squared from 0 to 6. And that turns out to be 96 Newton centimeters. Newton centimeters. I believe a Newton meter is called a joule. So this would be 0.96 joules of work. Okay. What do I really want you to know about Hooke's law? Because the College Board would have to spell out all of this for you. If they wanted to create a Hooke's law example, they would have to spell out for you exactly what Hooke's law is, and you would have to come up with the integral, et cetera, et cetera, et cetera. Excuse me. I want you to see that the work integral is just the same process we've been doing all along. Oh, okay. So, one more application, the normal curve. The normal curve actually has an equation to it. The normal curve is of the form f of x equals 1 over sigma times radical 2 pi e to the negative x minus mean squared over 2 sigma squared, where m is the mean, sigma is the population standard deviation. It can be shown that this function has a mean of 0. Well, it doesn't really matter. It can be shown that the area under this curve from negative infinity to infinity is 1, because the sum of all possible probabilities is 1. This function is how your calculator finds all those probabilities, where you would punch in buttons and say, what is the probability of getting between this number and this number? If this is the mean and that's the standard deviation, your calculator sets up the equation of a normal curve and integrates it. That's what it does. So, frozen spinach boxes have a mean weight of 10.3 ounces and a standard deviation of 0.2 ounces. What portion of boxes weigh between 10.0 and 11.0 ounces? So again, this doesn't seem to be terribly difficult. College Board would have to spell out that equation for you, but now you can just say 1 over 0.2 times radical 2 pi e to the negative x minus 10.3 squared over 2 times 0.2 squared. And then we compute the integral from 10 to 11 of f of x dx, and that happens to be 93.3%. Do you have to know the equation of the normal curve? No. You do have to recognize that if we were to graph the normal curve, let's do that. If we were to graph the normal curve, here's your 10.3. Here's 10. Here's 11. This area, and the area is a definite integral. That area represents the probability of the event occurring. So again, we use the integral as the area under a curve to help us solve a problem. And if you haven't been figuring out that integrals help us solve problems, then well, so that's it for Unit 6. That's all she wrote. I hope things are well with you and that we fine-tune things in class tomorrow. See you then.